Yeah, meeting is recording now. Hi. So this the last week was week 10th of complex analysis course, and here we are going to first, as usual, uh, short summary of what have been done in this week, and then we'll solve some exercise problems. Okay, so let's start. So this week, the residue of function at a point z, this was defined, and this was defined in a neighborhood. So if in a neighborhood you have some singular point, then at that singular point, so we get a Lorentz series expansion, not exactly in the neighborhood, but in a deleted neighborhood, and that deleted neighborhood is actually understood as annulus. So Lorentz series expansion is uh, given in an annulus. It is defined. So in this particular case, in deleted neighborhood case, the first radius is zero, and the second radius is something bigger than zero. Okay, so it becomes an annulus deleted neighborhood. Right. So in the deleted neighborhood, if we have Lorentz series expansion, and let me little bit explain what is residue. So you have a series expansion in a neighborhood, deleted neighborhood, sorry, and you take a curve which which is in the neighborhood and not passing through that point, and it is like a small circle around that point. Okay, and it within the neighborhood. Then what happens if you take integral? So most of the power series terms, they are like z constants, z squares, z cube, and so on. They are all analytic, right? So when you take integral, integral is linear, and these are because analytic. We can use Cauchy theorems. All the integrals are zero. Okay, in the positive degrees, all the integrals are zero. What happens in negative degrees? If you have, let's say, 1 by z square, what happens to this? This is a function, and if we take unit circle, for example, an integral of 1 by z square, what will happen? It will be zero. Why? Just because 1 by z square is also having anti-derivative. Okay, its anti-derivative will be uh, something minus 1 by z or something like that. Okay, and but what happens to 1 by z? So here z has degree 1. This is degree 1 polynomial in the denominator, and if you take antiderivative, it's in real case it is well defined. It is log of x. Okay, when you are given 1 by x, what is its antiderivative? Its antiderivative is log of x, but in complex plane it is not well defined. So that is why what I was telling, the if you have a Lorentz series expansion, big expansion, and if you calculate integral in a over a closed curve which covers that point, for example 0, and you are talking about path unit circle. So most of the terms like z square and so on, the power series terms, their integral will be 0 because of Cauchy theorems. But integral of 1 by z, this doesn't vanish. Okay, so in particular, if it was, for example, 10 by z, so what will be its integral? 10. So the coefficient of 1 by z, that gives us the whole integral of. So it is why here it is called a residue at that point. Okay, so that's the argument. You can listen it later. uh, so this is defined in the same fashion. So we have a big Lorentz series expansion, and residue of f at z naught is basically uh, coefficient of 1 by z minus z naught. Okay, so a minus 1 is the minus 1 coefficient of Lorentz series expansion. It is so when it is removable singularity, what happens? All the negative things, negative coefficients are zero, right? So only positive terms remains, and that is called Taylor series expansion of f. So when we have a pole, z naught is for example a pole, then uh, so it is something analytic function gz divided by, if it is m order pole, so z minus z naught to the power m. It looks like this. Okay, so the here, because it is pole of order 1, it is starts from uh, 1 by z minus z naught and then positive degrees. So only one negative degree here, because we have pole of order 1. So in this particular case, residue is a naught. Here is given pole of order m. In the other case, it is am minus 1, the coefficient of am minus 1, which is m minus 1th derivative divided by m minus 1 factorial. Okay. So here we have a residue theorem. If we have a closed curve, and in that closed curve, there are no poles, no zeros. So function is well defined in that closed curve, and the closed curve where it lies in a domain where our function is holomorphic, not everywhere, but leaving some finitely many points. In the finitely many points, there are poles. Okay, so kind of meromorphic functions. Then we can calculate the integral of f over this curve gamma, and the integral actually depends on residues at various poles. So here is the formula. So 1 by 2 pi I of into integral of f over gamma is summation of winding number of zj into residue of f at zj. So various points, we can add them and get the integrals. Winding number is, I'm telling you this, how many times the curve bounds the points. Okay, just like a general Cauchy formulae. If you remember general Cauchy formula, if curve is rounding your points only once, so integral is like basic formula, first formula which we have seen. But this winding number comes because curve may be crossing your points two times. So that's the point here, and we are not going to see the proof of this. Uh, okay, so of course, we are not going to see the proof of this, but let's see other things what we have seen. Log derivative of f for a meromorphic function. Uh, F is holomorphic function, then this is log derivative f prime upon f. Okay, so here we have some properties of log derivative of, if fg, then fg prime divided by fg is f prime by f, means log derivative of f plus log of derivative of g. Similarly, we have division formula for log derivative f by g. Log derivative of f by g is log derivative of f minus log derivative of g, like that. So, okay, I hope you have gone through the classroom. So I'm not going to talk in everything, but let's see this theorem, this principle, argument principle. Omega be open set in C. F is meromorphic function defined on C. Omega f has zeros of order d1, d2, dn at z1, z2, zn. After removing the removable singularities, f has poles of order e1, e2, ems at various points w1, w2, wm. gamma be closed curve which is null homotopic in omega such that zeros and poles don't lie on gamma. Okay, then what happens if you take integral of f prime by f? So it says the integral is exactly zeros minus poles. So zeros means all the zeros counted with multiplicity is the first part, the positive thing. The negative part is about poles. If function has, let's say function is holomorphic, then there are no poles. So this part will be zero. Okay, this part will be zero if function is holomorphic in the domain, and this integral will only count zeros, all the zeros counted with multiplicity. Okay, so this will be some integer number. Okay, okay. So we are not going to see the proof again for this, but we just assume that you have gone through the class and it is very easy. So this is one line kind of proof. Here is the proof. You see this. Okay, all depends on how it looks like. Okay, on the expression of log derivative. Now stability of zeros. Uh, we are not going to see this. So actually, if we have some condition on f, let's say f has n number of zeros in a domain, means in, in a open connected domain. Okay, and a little perturbation of the function does not change the number of zeros. So number of zeros remains as in the original function if we perturb little bit. So what is that perturbation? What is that condition? We can see here. So not here exactly. Number of zeros in the interior, counting multiplicity, same number of zeros. You have an so here in the picture it is clear. So if you take the green curve and the pink curve, so they are homotopic to each other. The homotopy, the the part of homotopy does not contains the zeros. So all the zeros are within the green curve. So if you say that number of zeros inside the green curve, they are same as number of zeros inside the pink curve. So that's clear from the picture. So we don't read the statements. We just see what is done here. Okay, and the proof and so on. Yeah. For example, here they have given some example. So z zero, sorry, z square. Z square is counting with multiplicity. It has two zeros within unit circle. Okay, zero counted twice. And what happens if you take z square plus epsilon, a little epsilon, very little? So it gives also two roots, but here we have different roots with all multiplicity one, I root epsilon minus I root epsilon. So this way, so function, if you add very little in a given holomorphic function, it doesn't change the uh, number of zeros in a curve, inside a curve. Okay, or inside a domain. Particular domain. The Rossi theorem is talking about that. So previous thing was lemma, and that lemma will be used in here in the Rossi theorem. So we remember the statements so that we can solve the questions for today. But for the proof, you have to go through the class very carefully. Okay, because I have not gone. I'm not explaining all the proofs. I'm just explaining the statements, and we'll solve exercise problems. There we will deeply understand how to solve them. Okay. Gamma B closed curve, which is null homotopic in omega. Suppose f and g are holomorphic in omega with some extra condition that modulus of g is always less than modulus of f in the curve gamma. Okay, then f and f plus g They both have same number of zeros counted with multiplicity inside that yes, curve. Okay. Okay. Uh, this term is technical. This term where gamma is null homotopic from. I'm telling you, if you have this curve gamma somewhere, they're talking about null homotopy from gamma to constant path means they're talking about this region where this homotopy happens. Means curve contacted to a given point. This homotopy region means the inside part. Okay. Okay, so that is what they are meaning taking here, and that's I think that's the end. Now they're solving some exercise problems. I think we are not going to say this. We'll solve our problems. So various tricks has been applied to calculate this infinite kind of integrals. We have to calculate. This is real integral. We change this to a complex integral, and then we use Cauchy residue theorems or other residue formulas to calculate the integrals that we can do it very easily using complex analysis. Okay, so let's go to our notes for today. So we here we have our first question. Let fz be e power minus z divided by z minus 2 whole power 4, and alpha be the residue of fz at singular point z is equal to 2. Then the value of 6 e square into alpha is. So we have to somehow calculate what is exactly this alpha means the residue. How to do that? So if we expand this function into Lorentz series, and then we calculate the residue. That is, there are other tricks, of course, but that is basic. Uh, we will use basic, very basics here, and we will calculate what is alpha. Okay, fine. So here we have e power minus z and z minus 2 whole power 4. So because singular point is z is equal to 2, we have to extend Lorentz series around this point in a deleted neighborhood of the point 2 is deleted. Okay, so we are talking about series expansion with powers of z minus 2. So the below z minus 2 the whole power 4, we are not going to change it. Okay, so that we are going to change for e power minus z minus z minus 2 plus 2. Okay, so fine, z minus 2 whole power 4. So this can be further written as e power minus z minus 2 minus 2 into z minus 2 to the whole power 4, and Then e power minus x has some x. So e power minus 2, let's take it outside, and z minus 2 to the whole power 4 outside, and expansion of e power minus z of minus 2 is 1 1 1 plus, here it is alternative, uh, 1 minus z minus 2 by 1 factorial plus z minus 2 whole square by 2 factorial minus z cube z minus 2 whole cube by 3 factorial plus z minus 2 power 4 by 4 factorial plus and so on. So I'm not going to write everything because we are how to focus only on uh, the coefficient of 1 by z minus 2. So if you multiply this z minus 2 whole power 4 in the denominator, what happens? E power minus 2 as it is, let's take it outside, and inside part it becomes 1 by z minus 2 whole power 4 minus z minus 2. Okay, it becomes 1 by z minus 2 cube plus 1 by 2 factorial z minus 2 whole square minus 1 by z minus 2 into 3 factorial plus something, but it will be 1 by 4 factorial minus something and so on. So we have to see what is quotient here, right? And that is the e power minus 2 will be of course multiplied inside. So here, from here what we get, this was expression for fz. So residue of f at 2 is nothing but minus e square by 3 factorial. Okay, and now we calculate what is the required calculation. 6 e square into this residue, this is our alpha. So we have to calculate 6 e square alpha. This will be equal to 6 e square into minus e square, so e power minus 2, sorry, so here it was e power minus 2 by 3 factorial. 3 factorial is 6 and it get cancelled with 6. E square get cancelled, and everything left is minus 1, and this is the answer. So this this is one way to calculate a residue, and uh, there are many other ways you can directly calculate residues. Okay, so we'll see if some kind of question comes, difficult questions will not able to express our power series very easily. Theory power minus z, we know them, so that is why we expand them and calculate them. In general we don't know power series expansion for big difficult functions, then we'll calculate using some tricks. Okay. Okay, so let's see the second question. Omega be a domain, Z naught is one point in the domain, Fz is holomorphic function in the deleted neighborhood, means not defined at Z naught. Gz be a holomorphic function, which of the true statements? Which of the following is true statements? Okay, so if Fz has removable singularity at Z naught, then something. So fz has removable singularity means we can assume f is holomorphic, because if it has removable singularity, we removed it. We can assume that it is holomorphic. Now G is also holomorphic, F is also holomorphic. What happens then? Residue of F into G is equal to G of Z naught into residue of Fz. Now, when Fz and Gz both are holomorphic, what happens to F into G? That is also holomorphic function, right? Right. So this is similar kind of algebra of differentiability, differentiable functions. F and G both are holomorphic, then F plus G is holomorphic. F into G is holomorphic, something like that. So F into G is holomorphic. Now we know. So you expand them into Lorentz series expansion. What happens? Because it was holomorphic, you get no negative degrees terms. So what happens? Residue will be zero. So the A part, F is removal singularity means holomorphic. We can assume holomorphic. We can assume, because again the same thing. Uh, I'm not going to write it because I have already told you what it is. F is holomorphic and G is also given holomorphic, right? So so is F into G. Hence, residue of F into G at what? Z naught. This will be zero because there are no negative degree terms in Lorentz series expansion for holomorphic functions. Okay, so a part, so on the left side we are getting zero. F into G is holomorphic, so residue is zero. On the right side, what we are getting? Residue of F at Z naught. Now we know F is also holomorphic. So this residue of F at zero is, Z naught is also zero. So both sides are zero, as well as residue of F at Z naught. This is also zero because same logic, F is holomorphic. So A is true. Now we are going to see second question. So the second part of this, uh, FZ has removable singularity and ZZ naught is non-zero. Then the same question means the above equality will happen here or not. FZ has removable singularity at Z naught. This means that F is holomorphic. We can assume that. Okay. Then again, this left side is zero with the same assumption, and same thing. This part left side is zero. You know this from A. What happens to right side? Gz naught is non-zero is given to us, but this residue of half at z naught, this is zero. It is non-zero, no problem. But the other multiple is zero, so the equality holds again, and this is true. Okay. I'm not going to write this. We are using this part A only. Right. Now the third option, if Fz has simple pole at Z naught, then Fz has simple pole. Then let's see. The same question is asked. Let us write something. Okay, then we'll calculate them. This is for part C. Fz can be written as f, not f, we can write h maybe. Hz, which is holomorphic in the domain, divided by z minus z naught. Because they have said that this pole is simple. So I'm writing z minus z naught to the power 1 only. Otherwise, we could have write some weird power also. Now, Fz is of this form where Hz, this function is holomorphic in omega or on omega. Whatever. Uh, Now we have to calculate residue of f into g. Okay, let's see. G is some already holomorphic function. So G has Taylor series expansion. Uh, this also Fz also has Taylor series expansion at Z naught. What is that? So G of Z can be written as G of Z naught plus something, that something is G prime Z naught by 1 factorial into Z minus Z naught. Okay, plus G double prime at Z naught divided by 2 factorial Z minus Z naught to the whole square, and so on. This Taylor series. Let's write for Fz also. So Fz can be written as, sorry, but there will be some issues. Okay, it will be something, let's say, a naught here divided by z minus z naught plus a1 plus a2 z minus z naught and so on. Right, like this. Okay, because it has simple pole, there will be one negative term in Lorentz expansion. We don't know coefficients a naught, a1, a2, and but we are writing them. Now what happens to f into g? F into g of z, this power series. Can you multiply two power series? Two formal power series can be multiplied. And what will be the negative degree term here? The only negative degree term will be coming from multiplication of first terms in the power series. Okay. So what will be that? This will be a naught into g of z naught divided by, yeah, z minus z naught. So a naught is residue of f. Okay, plus something, plus some holomorphic function. Okay, I'm writing this some holomorphic part. Right. Now we have calculated some expression for f into g, and we'll see the third option. Third option was that if f has simple pole at z naught, we are calculating left side first, residue of f into g at z equal to z naught, and that is exactly um, this residue of f into g at z naught is a naught into g of z naught. From here, so how I'm directly writing this, we have already explained that residue is defined this way: the coefficient of negative first negative term, okay, a minus 1 in the Lorentz expansion. So here it is, this part. Okay, right hand side, what right hand side says, g of z naught into residue of f at z naught. So what is residue of f? This is residue of f at z naught. Residue of f at z naught and into g of z naught. So this is correct. So the third option is correct. If you have any doubt, you can ask it. Okay. Otherwise, we'll see next option in the same fashion. Okay. If fz has simple pole at z naught and gz naught is non-zero, then same equality they are talking about. Gz naught is zero or non-zero, doesn't matter. You see in the proof, if it was zero, what have been the difference? There will have been no difference. So in that case, there will be no negative term, and this will be zero. So this is true. Either gz naught is zero or non-zero, doesn't matter. Okay. Why? Because if gz naught was zero, then also negative terms, the only one negative term will come, which will be the product of first terms in the power series expansion. Here, this one and this one is zero, non-zero, doesn't matter. So the uh, fourth option is also correct. Uh, we can write gz naught being zero or non-zero does not matter in the negative degree of f into g. So we have another option left here. Right, last option. If object has pole of order bigger than 2 at z naught and g z naught is non-zero, then restive of f into g at z naught is equal to, again same question they are talking about. So what change we require? F has pole of order m. If f has pole of order m bigger than 2, then f will look like of this form. So let me change uh, e option. F has pole of order m which is bigger than equal to 2, then fz will be looking like this: a minus m divided by z minus z naught to the power m plus a minus m plus 1 divided by z minus z naught to the power m minus 1, and so on up to a minus 1 divided by z minus z naught plus a0 plus a1 z minus z naught, and the positive degree terms. Okay, f looks like this. Now what happens to f into g? F into g we can directly see from here. So when we get here, we have this part is only required. We don't need to know anything else than this part, the first negative degree term. Okay, fine. For f into g, what happens? How many ways this can come? This negative degree term. So in g, you have to multiply this. So so this will be this first negative term in, I'm writing directly. Uh, Let me, first negative degree term in Laurent series expansion is, what is that? A minus 1 by z minus z naught into g of z naught. So z naught. Okay, whatever pronunciation is there. Plus there will be more. What will be more? Uh, a minus 2 will be multiplied to this number, a minus 2 g prime at z naught by 1 factorial, right? So when you multiply with that, so a minus 2, it is divided by g minus g naught to the power 2, and g prime g naught, it has positive power 1, so 1 power is remains downside. So and so on. Here also we remain z minus z naught in the denominator. A minus 3 g double prime z naught by 2 factorial. Here also we remain 1 power in the, and so on. This goes to a minus m, a minus m uh, divided by z minus z naught, z m minus 1, something like that, at z naught by m minus 1 factorial. So we get this big number, and here it is said that this is what is left hand side. Now we can calculate residue of f into g at z naught. What will be that? A minus 1 g of z naught plus a minus 2 g prime at z naught plus a minus 3 g double prime at z naught by 2 factorial, and so on. Some big number, okay? And what they're saying, is this equal to a minus, so residue of f into g of g naught, is this equal to this number? In the first thought, what will you tell? That these two are not equal. So what happens? This part has to be zero. They are saying this is zero. Is this always zero? No. So this is left hand side, you know, and this is what? Residue of f at z naught into g of z naught. So question is, are these two equal? So their question is this box number is zero? And the first answer will be no. You can create some counter example. Okay, we will create some counter example. If you wish, we can create, or we can leave it at this point, because we have uh, we can take something which is where these numbers are non-zero. What do you say? We can leave it, or try to give some counter example here. uh, okay, so we can, I think we can try some counter example, basic counter examples. G, we have to take identity, sorry, holomorphic function, and F has to have some pole of order bigger than 2. G of Z naught is non-zero, and I'm telling this will be wrong. So some counter example of, so I'm leaving at this point. I think we can get some counter example where these numbers are non-zero. Uh, you can give me some counter example. I think, mm, if I'm taking 1 by z, sorry, 1 by z is square, so the residue at 0 will be 0. So the right side will be 0, doesn't matter. While on the left side, we don't know. So we can get some counterexample with this construction. The simple answer is no. Uh, you can create some something where it is not zero. Okay. Okay. So leaving at this point in this question, this is wrong option. We can see next question now. Uh, Next question, question number 4 or yeah, 3 first. So this question is about calculating the residue of some function. Mm, we have already told you again and again what is residue, uh, because you were not present in the starting of the session. I'll explain what it is. Some meromorphic function is given, and in a deleted neighborhood we can get a Lorentz series expansion for given holomorphic function. And in the Lorentz series expansion, most of the terms are analytic. For example, z square, z cube, these are polynomials, and integral commutes with integral is linear function, so it goes everywhere. So most of them are zero because of Cauchy theorems. Cauchy theorem still, if some function is holomorphic in the domain, and for the closed curve, integral will be zero for them. And but what happens to 1 by z? First negative term. There is the problem. So most of them have antiderivative. They have antiderivative, so they are infinitely differentiable future in future also. But at 1 by z, its antiderivative is expected to be log of z. But log of z is not well defined function in the complex plane. So its integral is not vanishing. Its integral is exactly for unit circle. If you take in the Cauchy formula 1 by 2 pi I into integral of this 1 by z, it becomes 1. So integral is non-zero here in this first negative term. So this is why first negative term is called a residue of the function at that point where it has a residue. It has pole, sorry. Fine. Now we are coming to third question. We have given some condition on function, and we have to calculate residue at 0. And function is defined in d minus 0. Unit disk minus 0. Okay. So what is function? They say that if you put minus z in place of z, they agree. So these kind of functions are called even functions. Even functions, if you expand them into Lorentz series expansion, what you get? Only even terms, even degree terms you get. No odd degree term. So you can write them explicitly. How? Let fz be summation z to the power n, n varying in integers, or some quotient we have to write, of course, a n z n. Okay. Then if you put f minus z, what you get? N belonging to z, again an as it is. In place of z, if you put minus of z, what happens? uh, Minus 1 to the power n comes out, and then zn. And this minus 1 to the power n, when it is odd it is minus, when it is even it is plus. So it will be taken into two summations. When n belonging to 2z, it is an z to the power n, minus when n belonging to 2z plus 1, this is an z to the power n. Okay. Okay. So there will be some issue with the subscript, so I running So I is also called iota in complex space, so I is also not good. Let's say k is running, okay, in odd integers. Okay, so now the first power series, okay, agrees with the second, this one. This is condition given to us. If these two are equal, what happens to them? So this part is equal in the both side, it gets cancelled out, okay. What remains is 0. So from here what you get, this implies summation a n z to the power n belonging to 2z plus 1, this part. Not here it is written k, so we can make it k. There's no issue with that. This is 0, and this implies odd degree terms, their coefficient is 0. No odd degree term in the expansion of f. Okay, so from here what you get? What will be a minus 1? Means first negative degree term. This will imply that residue of f at 0, this will be 0, because the residue part comes from first negative term and first is an odd number. Okay, so this way. So the first option is correct, but when first option is correct, the second option is incorrect, because that saying that the residue is plus 1. Now we are going to see third option. In the third option, we have some other condition which is about odd functions. F of minus z is minus of f of z. In this case, they're saying that residue is 1. Is this correct? Okay, let's see what happens to series expansion. Just in the previous trick, we are going to apply here also. We have series expansion for f. You replace z by minus z. So you get the second thing. Okay. The first thing is this. Second thing you get this. Now you have to multiply by minus, because here we have extra minus. So when you multiply by minus in the first, the negative term get cancelled. These odd degree terms get cancelled. What? No, no. They survive. Okay, which term survive? Only uh, in the odd case we have only odd terms. So in the second part, this is C. Sorry. Um, fz f of minus z equal to minus of f of z. This implies only odd terms are there in the Lorentz series expansion. But we don't know what they actually are, right? They survive, odd terms survive, but what they are, we don't know, right? So we cannot say what its residue is. For example, I'm giving you one thing. Uh, this you take 1 by z or 1 by minus z. This is our f of z. If you take f of minus z, what you get? 1 by minus z. But this is what? Minus outside, inside is 1 by z, and that is f of z. So this is an odd function, right? Its residue is 1. What happens if we change it to 2? 2 by z. So again, it is an odd function. Its residue will be what? 2. So it is not fixed. We know at least that. There are odd degree terms in the power series expansion, that we know. and we don't know what coefficients are, right? So we don't know what residue is in this case. But in the even case, we know that, because no odd degree terms means that is given to be zero. First negative degree term is zero, but here it is not the case. So we got that this is incorrect option. It can be anything, not necessary. It can be anything in particular. So now fourth option, for each a belonging to C, there is holomorphic function fa on d minus 0, unit disk minus 0, which is odd. F of minus z is minus of z, and the residue of f at z is equal to 0 is a. For each a in complex plane, there exists some function which is odd. So, oh, I just as in the previous case, I was giving to you an example of something. Is the they are what asking the same. So of course, for any C, what we'll take, or any A belonging to C, A by J minus at what point? 0. A by Z. What will be residue of this function? This is, let's say, this is my f of Z. This is an odd function. It depends on A also. Its residue will be A. Okay. So any complex number will be occurring as residue of this kind of functions. We have calculated. We don't know to check anything after this, because for every point A we have calculated what function is. There will be more functions, but we don't care. Okay, because they are saying that there exist. So we give one and we are done. So this is correct. Just to could be anything. Now last option, if f has pole at z is equal to 0, then residue of f at z is equal to 0 cannot be 0. Uh, will you try to answer for this? They're saying that f has pole, but the residue cannot be 0. Is there is some residue always? Not necessarily. I'm telling you. You look for this function. Fz is equal to 1 by z square. What happens to if you take residue of this? It will be 0, because there was no first negative degree term. This is second negative degree term of the expansion. What happens if you take Lorentz series expansion for this function? There will be no Lorentz series expansion. The same function will be Lorentz series expansion for this function. Okay, 1 by z square only. So there is no first negative degree term. So we are done. This is a counter example, right? Means pole. It has pole, but it can be 0. Residue can be 0. Sorry, can be 0. Means this is wrong, because they say that cannot be 0. Okay, now we have two more questions left to do, and I would like to know which question to do first. We have a closed circle of radius 4. We have to calculate sum integral first thing. And the second question is about simple zeros and what? Yeah, this Ross's theorem, where they're saying that if you perturb little bit a given function, number of zeros counted with multiplicity that do not change in a given given inside of a circle or inside of a path, closed path. Okay, let's see first fourth question, then we'll solve last question. We have four radius curve circle around origin. Let's draw that. Let's think that this is 4 radius circle and this point is 4 and this is 4i, this is minus 4i, this is minus 4. Assume that 4 radius circle it is, and we have this function is our function is 1 by fz is, if you compare with cos integral formulas or whatever, the fz will turn out to be 1 upon z sine z. Now you tell me at what point this is not well defined. This is not well defined at points exactly where denominator is 0. Denominator is 0 where it is 0 when z is equal to 0. First of all, it is 0 when sin z is 0. So we have to check when sin z is 0. Sin z is 0 exactly when z is equal to n pi, means multiples of pi. So how many pi multiples are inside this unit, this disk, inside inside this circle? This is your gamma. How many multiples of pi are there? 1 pi, 2 pi. What is 2 pi? Pi is bigger than 3. And if you multiply by 2, it becomes bigger than 6. So that is not inside. So somewhere pi is here, somewhere minus pi is here, and 0 is here. So only 3 points are there, which are poles or singularities, simply singularities. There are 3 points of singularities. Now we have to calculate. This is, this integral is, we are going to calculate by residue theorem. We have told you that see where are poles, calculate the residues, add them up, and then we are done. Now here winding number is 1, so winding number is not mattering to us because this circle is winding these points exactly once. Okay, if it was, for example, here it was 4 pi, what happened to that? Then it binds 2 times, so we have to multiply by 2 extra. So that is not the case here. It is 2 pi, so binding number is 1. We are not going to take care of that. So integral of this is 1 upon 2 pi I dz upon z sin z for gamma is exactly sum of residues of f. This is our f at this let's say this is z1, z1, z2, z3, zi, I from 1 to 3. So z1, zi is nothing but, I'm talking about this minus pi, 0 pi. Now we calculate residue at various points. Residue of f at 0, what happens to this? Because I have seen this function already, I can tell you that sine function is an odd function, cos function is an even function, 1 by z is an odd function. Multiple of two odd function, what happens to that? That function become even function, right? Because when you put f of minus z, it becomes 1 by minus z into sine of minus z. But sine of minus z is minus of sine z. Minus minus becomes plus and it becomes f of z only. So fz is an even function. And we have seen that just in the previous question maybe. For even function, restive is 0 since fz is an even function. Okay, this residue calculation was pretty easy. What happens in other cases is maybe difficult, but not that difficult. Residue of f at pi will calculate for pi, maybe minus pi will be, we can directly write from the calculations. Okay, how to calculate this? We have to expand our function around z minus pi. Will that work? Let's see. We'll do that. Mm, we have here 1 by, let's start from right side. 1 by z sine z. This can be written as 1 by z minus pi plus pi. Okay, so after this, we have some multiple also sine z, and sine z minus pi. What happens to that? Uh, what can be written? Okay, let's calculate in the right side. What happens? Sine pi minus z is equal to, so the graphs are like this. Both are positive, so it will be positive, right? I was doing some basic calculation. This is sine z only. So sine z minus pi is minus of sine. So there will be one minus thing. So we can write uh, minus 1 by, we can take pi common, then it will become 1 plus z minus pi divided by pi into sine z minus pi, something like this. Okay. So okay. I think this will not work because uh, let's say 1 by sine z another expansion, and this part is another expansion. So we'll do it in two parts, and that will be, I think, easier to do. So I'm saying we'll do this part only and then multiply them. This is for 1 by z. Okay, 1 by z can be written like this, and for 1 by z we'll get some expansion. So the domain matters. it, where is the domain of this? Z minus pi. If the center is pi, and divided by pi means this circle there. In this circle we have expansion. Okay, so in this red circle we have some expansion, but we don't need expansion everywhere. We need in a little neighborhood of pi, which is inside our domain. Doesn't matter. Okay, so we are getting in some bigger expansion, so then also we don't care. But in the neighborhood we need, and that is what we are doing here. This is not minus one; it was plus one there. So it is 1 by pi, and then multiplied by 1 minus z minus pi by pi plus z minus pi by pi whole square minus z minus pi by pi whole cube plus, and so on, plus minus, it goes way in the same pattern. Now we'll write expansion for 1 by sine z. So we are going to calculate at pi. So sine pi value is, what happens to sine pi? Sine pi is 0. So the first term is 0. Wait, doing the series expansion. There is something missing. So in the, how to write power series expansion for this? Someone of you can tell me if you know. Uh, so usually what happens? F of z naught plus something and so on. But here it is not. So yeah, I'm trying to expand only. Uh, how to expand this 1 by sine z? Usually starts from f of z naught plus uh, from the denominator how to go to numerator. That is also needed. So this the idea you are telling is already used here in first part. 1 by z in the expansion of 1 by z. In the expansion of sine by 1 by sine z we need. Huh. Now I how to do that. Let me see. Give me a second. So the trick is this: uh, sine 1 by z into sine 1 by z. This, okay. Let me delete this part. Z sine z. This can be written as 1 by z. Wait. Okay, let me write is 1 by z as it is. 1 by sine z, this will be z minus z cube by 3 factorial plus z power 5 by 5 factorial plus, sorry, minus, plus minus and so on, continuously. This is in the denominator. How to send them into numerator now? So take z common and cancel out by this below z. Oh no, no, sorry, that is exactly in the denominator. How can that be? uh, but we have to expand around pi. That is also we have to take care of that. So minus we can take here, and it becomes z minus pi. So this is z minus pi everywhere. uh, okay, till now it is fine. So here you make plus, you can make minus this way. Minus you have to take here, sorry, a mistake. This is uh, 1 by z sine z. We are writing in some other fashion so that we can calculate its residue. we, I think we could use some other tricks. Okay, what to do after this? Two power series, one in the numerator and one in the denominator. So this series is calculated very explicitly. Uh, Only first few terms has been calculated, not all of them. Idea 1 is equal to sine z into 1 by sine z. Known Taylor series, unknown Lorentz series. This is this question is very deep. There are some things to do, right? Uh, what exactly is that? So okay, we have to inverse a power series. How can we do that? So after multiplying two power series, you have to get one. So the constant degree term should be one. Others, all the other entries should get cancelled. Okay, this way I'm telling you one trick how to do that. This power series, whatever it will be, first term will be 1 by z minus pi. Why? Because when you multiply these two series, you have to get 1. So this term is there. Fine. We don't know other things and we don't care about them. Why? Because we only care about first negative degree term, first negative degree term, that is this 1 by z minus pi. Okay, plus something, some negative degrees, some positive degrees, some other part. Okay, some more part, some more terms. This is inside the box. 1 by sine z minus pi has this expansion. Okay, 1 by z minus pi plus some more part, we don't care about them, no worries. Now minus 1 by z, what happens to this? Minus 1 by z can be written as z minus pi by pi, uh, pi taken outside 1 plus. So we do this and we expand this also. What we'll get? We'll get minus 1 outside, minus 1 by pi outside, and inside part is 1 minus z minus pi. Think about this. Okay, let me see if we have. I think we have got it correctly. Z minus pi by pi plus z minus pi by pi whole square, and then minus, and minus and plus it goes away. So here, from there, first negative degree term is 1 by z minus pi, and here uh, constant term is minus 1 by pi. So you multiply them. What you get? Other terms we don't care. They will give you positive degree terms. So, yeah. So first negative degree term of Lorentz series expansion of 1 by z sin z around pi gives, so each, what is that? Minus 1 by pi from the this part 1 by z part into 1 by z minus pi plus some more from here, minus 1 by pi from here, and 1 by z minus pi here. Okay, so my computer has been shut down. Is my screen visible and I am audible correctly? Am I audible? I hope so. I'm audible. Uh, let's see. Uh, this is the first negative degree term. And from here, this implies residue of f at pi is minus 1 by pi. Okay, so then now we have calculated this residue. What happens if we take at minus pi? Sorry, yeah, at minus pi this becomes minus pi everywhere, and you have to take here
then there will be no minus 1 by pi. Similarly, residue of f at pi, this will be 1 by pi, because this minus 1 by pi comes, sorry, this minus appears when you take, here we had some calculation, sin z is equal to minus of sin z minus pi. So if you calculate uh, sin pi minus z, or sorry, pi plus z, and minus taken outside completely, this will be uh, sin z in minus. So at minus pi, if you want to expand them, so you have to take z minus minus pi, and this will be this, and you will get one minus thing. Right, you are getting again minus sign at both points. It is same residue. What? Okay, let's see more clearly. What is change we are doing? Sin pi minus z. This is sin z. So when you write z minus pi, then you have to multiply by minus. So this is minus of sin z minus pi. Okay, so one minus appears here. What happens when we take sin z is equal to sin, we need z plus pi, pi plus z. This is already minus. So it is again in minus. So one minus already appears in both cases. So this is minus of sin z plus pi. Okay, this is the way. दोनों में we are getting same residue. So what will happen? What will be the integral? So minus 1 by pi minus 1 by pi. It will be 2 by pi, right? The integral is expected to be 2 by pi. So actually, I have got some problem here. Stuck in simple question. So in the both cases, we are getting same same 1 by pi. I don't know how. So if it was needed z plus pi, then you have to add, and here it would have been plus. Everywhere in the expression of 1 by z, it has been all positive degree, all terms positive. So why minus 1 appears is because of sign problem. sine z, 1 by sine z. Right. So we have calculated these residues. Now all of them you have to add them. So overall this integral will be minus 2 by pi. I think there would be some mistake because uh, we actually got an integer solution. There are little mistakes in calculating residues. I don't know actually order of the poles. So 1 by sine that is unbounded. So unbounded or bounded? It is unbounded because at pi it becomes 0 and it is unbounded. So it looks like it is an essential singularity. And at an essential singularity, we don't know residue because residues basically defined they're defined for they're defined for essential singularity also. We have to just see what is first negative degree term. Mm. The minus term is already there and 5 plus z minus 5. 5 का क्या ठीक है. So if it was at plus 5 what's needed. Oh, 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 I see. So the problem is here at this step here. I made something else and it becomes heart or symbol. Okay, we'll do here. There is some issue in the second case when we have to expand like z plus pi to the power k. This sum ai. Then at this level, you have to what you have to do. 1 by z can be written as 1 by z plus pi minus pi. Okay, and what you have to take minus pi common, right? Minus pi, if you take common, minus 1 by pi is written here, and what you take, it becomes 1 minus z minus, so z plus pi divided by pi, and so on. So 1 minus you are getting here is from here only, and 1 minus is coming from this sine z. So those two minus they become plus. So it was plus. Okay, you understand? The 1 minus thing is coming from 1 by z only. When you are trying to expand around pi, you have to sorry minus pi. You have to expand in the powers of z plus pi, the powers k. So to make that possible, what you did is this: you have taken minus pi common outside. So this remains together. Z plus pi remains together. So minus 1 in place of minus pi, it becomes 1. So you get good expansion. Now you can expand them. So in the second part, this is for first part, residue at pi you are calculating, then it is fine. But at when you calculate as minus pi, this is for minus pi, you get in the plus, and overall integral will be 0. Okay, so this was wrong. Sorry for that. Now I think it is clear to you. So how I did? I write this function into two terms, 1 by z into 1 by sine z. 1 by z can be expanded in this fashion, and 1 by sine z can be expanded this way, but we have to take inverse of that. Inverse means what? Some power series, which after multiplying with this gives us what? 1. So we understand that there will be some term of this form to make this constant term to be 1. Okay, and some more negative terms, positive terms, uh, power series means, of course, positive degree terms, they require more of most of most of them, but some more terms. So we just calculated here first negative degree term and here constant term, because all of them are positive degree terms. So this constant term is minus 1 by pi and then multiplied together, and we get this. And from here you calculated residue of f at pi, and then similarly you calculated it minus pi, there you will get plus, and hence the integral will be 0. Okay, so this question was little tough to solve for that. I think next part is easy and we'll do quickly, finish it, and then we'll leave. Okay, so fifth question is about f and g holomorphic functions on open connected subset of complex plane which contains a unit disclosure. Suppose f has simple 0 at 0, simple 0 at 0, then f can be written as fz can be written as z into uh, sorry hz something hz, such that hz is non-zero, h0 is non-zero. We would write something like that. So simple 0 means only one zero with multiplicity 1. F does not vanish in at any other point of declosure. Check the boxes corresponding to which true statements are given. So the first inequality they talking about is this: epsilon into gz is always less than fz for the z running on unit circle, satisfied for epsilon is small enough. What if it is not satisfied? What will happen? So the first is if not. If not, then what? For any epsilon, however small, this is failing. So for epsilon n is equal to 1 by n, the inequality fails. The inequality fails. This means what? There exists Zn inside where unit circle. Unit circle means del d. Boundary of the unit is such that epsilon into g of Zn, this this modulus is bigger than modulus of f Zn. So we have got various points Zn where the inequality fails. One more thing. So unit circle is closed bounded subset which is compact, and Zn is Zn's are countably many numbers inside them. So there exists convergence subsequence of Znk, right? So what happens to them? uh, choose Z and K subsequence which converges to some point which is convergent something, right, something like that. Then for this convergent subsequence what happens? Z and K goes to some point Z naught, right, and G of, sorry, epsilon into G of Zn, where it goes, this goes to zero anyway. Why? Because G is continuous function and epsilon is going to zero. G of Gn is going to some particular number. Sorry, Gnk. This goes to some particular number, but where epsilon n goes? Epsilon n. So here it is epsilon n. Epsilon n goes to zero. So this goes to zero. But what inequality tells? This inequality. Star tells that modulus of f of z not this is less than or equal to 0. This implies f of z naught is 0. And this is the contradiction for what? This line. No other, when it says nowhere else in the unit disclosure, it has simple 0 at 0. And when it says nowhere else in the D closure, in unit circle is the part of that. And G naught belongs to del D. Because del D is compact, circle is compact, and any sequence inside them, if they converse inside them, means they converse the point lying inside the circle. Okay, so there we got a point where fz naught is 0, f is 0 at the point. This is a contradiction, so this inequality holds for smaller case. Epsilon is small enough. What happens to next? For epsilon positive, function f plus epsilon g does not vanish for any epsilon positive. Let's say epsilon is 1. And what if we take f is equal to minus sorry, g, uh, what if g, we can take minus f by epsilon, something like that. Function vanishes everywhere in the domain, not only on unit circle. So this is wrong because on g we have not given any condition about g. G is just some holomorphic function. Okay, so this is wrong. Why? Because if g has been taken this way, this function vanishes everywhere. How can one say does not vanish on unit circle? It vanishes everywhere, right? So in the same fashion, this option is correct, D option, because they're saying that unique zero, no, not necessarily unique zero, right? We can take something, some g, just like in the B part here, and it vanishes everywhere. Unique doesn't make sense now, right? Okay, good. So how about part C? For epsilon is small enough, the function f plus epsilon g does not vanish on unit circle. For epsilon is small enough, f plus epsilon g does not vanish on unit circle. Okay, for epsilon is small enough, we use part A and we calculate something. Okay, what is this C part? For epsilon positive is small enough, we know what? we know by a part that what happens? Epsilon gz is less than epsilon gz. This modulus is less than fz. If z naught is one point on unit circle such that f z naught plus epsilon gz naught is equal to 0, then what happens? Then modulus of f of z fz naught, this is equal to modulus of minus epsilon gz naught. This is exactly same as epsilon gz naught, modulus of them. But what happens? A part, this is contradiction to a part. This this is contradicting a, because there we had strict inequality. You see, strict inequality, and here we are getting equality. So there is no point where it vanishes. This function f plus epsilon g vanishes. So this vanishes nowhere on your circle. Does not vanishes on it. Right. This option is correct. Does not vanishes it on your circle. If it vanishes, it creates problem. Right. If it vanishes, then there is contradiction. So it does not vanishes. So now the very last option, and after this we'll go for epsilon positive small enough. F plus epsilon g has 0 in D. Moreover, 0 is simple. That is, order of 0 is 1. Right. Now we use A, and Rossi theorem is what is the statement is. So number of zeros of F. So what is Rossi's theorem? Last option. Some open connected subset of complex plane F and G, some holomorphic function, everything. Assuming all that, the hypothesis, if the main thing is this, if modulus of g z is less than modulus of f z on some boundary, maybe, okay, on the disk, let's say unit disk, del d means for every z in del d, then number of zeros, not exactly zeros, and poles also there, number of poles, number of zeros, everything they were zeros of f in d is equal to zeros of f plus g. So on the boundary, if g is less than f, then zeros of f is equal to zeros of g, number of zeros of. So this is what the correct statement is using a and process. Okay, today we have almost done 2 hours, and we'll see you next week. Bye bye. Do you have any doubts you can ask, or